Welcome back to ECE 207. What we want to do in this session consists of two goals. One is to work a problem that illustrates what you can do when you have two loads, and we are working with complex power, meaning our loads will have potentially real parts and complex parts, and we'll then have average power and reactive power, and we can then have this complex power quantity. Then we will look at another situation that is referred to as power factor correction. Can you now add an additional load that effectively brings the power factor closer to 1 or closer to the ideal of having the power factor equal to 1. We'll start with the two-load power problem, and here is the example which in the last session was introduced. We didn't get all the way through it, so today hopefully we will finish this problem up. We have a transmission line that has a pure resistive behavior, and we're modeling that resistive behavior as a resistance of 0.1 ohms per mile. The plant, or the first load, is 1 mile down this supply line, and at the plant, or at the first load, we know that the line voltage is 480 volts at an angle of 0 degrees, and that 480 value is an RMS quantity. We're also told that the plant itself consumes 120 kilowatts at a power factor of 0.85 lagging. That now tells us that we have an inductive load, and we can tell a little bit more about that. We can find the angle. We know that the average power, since it was given in kilowatts, is 120 kilowatts. That's the average power consumed by that load or the plant. What we want to know is, now that we have some supply delivering power to not only the load, but it also has to deliver power to the transmission line, we want to know what is the voltage at the supply side of the system, where we now have to supply the transmission line and the load number 1. And we want to know what's that voltage and what's the power factor at the supply side of the line. Here's the picture that we sketched last time. We have our transmission line, which is 1 mile, and the resistance was 0.1 ohm per mile. Thus, we have a 0.1 ohm resistance in between the supply voltage, which we're labeling or modeling as V sub S bar, and the plant, which is our first load. And we were also told, so let's say that this is now load number 1, and we were told that this voltage was 480 volts at 0 degrees RMS. And let's go ahead and just call this V sub 1. And that's an RMS quantity associated with load 1. We also have a current going through or supplying that load. We could call that I1 bar. These are complex quantities. And this transmission line is what we will call our second load. There's load number 2, and it also has a current supplying it and a voltage drop. Let's say V sub 2 bar from left to right, plus to minus. Now, what you should be able to see, since this is two loads in series, the current going through both loads is actually the same, and I may call that just some RMS current, I sub RMS bar. Again, what we're wanting to find is this voltage, V sub S, and the power factor associated with that voltage. Let's go ahead and write that down. This is now what we want to find. We want to find V sub S bar and the power factor associated with that particular supply side location for the voltage. We could do this many different ways. Let's look at it maybe a way that was slightly different than what we talked about it in the last session. If you simply wanted to analyze this circuit in the classical way that we've been analyzing even before we started talking about power, you might say, well, I could write a KVL around that circuit relating V sub S, V sub 2, and V sub 1 and find a relationship for V sub S. Meaning now with KVL, we know that, and these are complex quantities, minus V sub S, since let's start at this particular node and now go clockwise around that loop or mesh, plus the voltage dropped across this lumped model of our transmission line, V sub 2, plus V sub 1, and that's the voltage dropped across our load number 1, and we were given that particular voltage. That was 480 at 0 degrees. What we want to do then is we want to find V sub S, which solving for that says that that's V sub 1 plus V sub 2, or if we can now find V sub 2, we will be able to add that to what we already know of V sub 1 and find V sub S, which is one of the quantities that we want to have. And if we find V sub S as a complex number, then if we know the current flowing through the circuit, we can now find the power factor associated with the combination or the total of the loads 1 and 2. Now remember what the complex power formula or expression is. That's this complex power S is equal to V times I complex conjugate, and we can actually do that for each of these different loads. If we do it for load number 1, we have S sub 1 bar is equal to V1 I1 star, which is now V1 I1, or the magnitudes of those, cosine of, let's say, theta sub 1, where theta sub 1 is the voltage across load 1 minus, or the angle of the voltage minus the angle of the current, plus J V1 I1 sine of theta 1, where this first real piece is the average power of load 1. The second piece, or the plus J, is the reactive power of load 1, and we were given some of this information. We were told the average power of load 1, P1, that was 120 kilowatts. We were told what the magnitude of the voltage across that load was, V1. We don't necessarily know what I1 was, but we were told the power factor of the load, which is really cosine of theta 1. Here is power factor 1. We were given that, we were given this, and we were given that. Now we know what the magnitude of our current is through the first load, or load 1. That's now I1, which is this IRMS, and I can find that by taking P1 and dividing by V1 and power factor 1. Or this is now 120 kilowatts divided by 480 and 0.85 to give us a magnitude of the current flowing through load 1, which, since it's in series with load 2, also gives us the current through load 2, and we now know that the magnitude of that current is 294 amps. Because we know that the power factor is 0.85, we can now find the angle of our current. We know that cosine of theta 1, which is power factor 1, was given to us as 0.85. We can now solve that for theta sub 1. Theta 1 is the inverse cosine of 0.85. And if we do that, and what do we know? We were told it was lagging, which allows us to then not worry about, well, make the sign positive because we had a lagging power factor for load 1. And that means that we have an inductive load for load 1. Theta 1 now becomes (31.8 degrees). Now we know theta 1 is the difference between the voltage angle of that load and the current angle of that load. We've just computed theta 1. That's this 31.8 degrees. We know what the voltage angle was. That was 0 degrees, and now the only unknown is theta sub I1, or I'm sorry, theta sub I1, and this now becomes minus 31.8 degrees, and that's now the current angle of our system. Since it's in series, it's the angle of all of the currents. That's the complex RMS current, which is I RMS at an angle of theta sub I1, and that's now 294.1 at an angle of minus 31.8 degrees. Let's now look at load number 2. Load number 2, remember what circuit we had. We've now determined what I1 bar is. Now that we know I1, which is also, because of the series connection, that's equal to I2, we can now find V2 by simply multiplying I2, which is I1, times the load number 2's impedance, which in this case is a pure resistive load, but we can think about it for now in a general sense. If we look at load number 2, which is the model of our transmission line, we have Z sub 2 in general is the resistive component of that impedance plus J X sub 2 being the reactive part of that impedance. But we know in this particular example that R sub 2 for 1 mile of transmission line is 0.1. We were assuming no reactive component to the transmission line, and we now have then load number 2 if we were modeling it something like this with R sub 2 and L sub 2. If this was load number 2, we now know that Z sub 2 is equal to R sub 2 plus J omega L, which is the impedance of that inductor. But we were told, or we were given that load number 2 was purely resistive, and that tells us then that the inductance is indeed 0 in load number 2. But from this information, we can also now use our complex power expression and see that we now have, we can do this many different ways, I guess. We could say that the voltage of, maybe I should just do that. The voltage now for load number 2 is now Z sub 2 times I sub 2. But because of the series connection, this is now just Z sub 2 times I sub 1. Now we have that Z sub 2 is 0.1 times I sub 1 bar, which is this 249.1 at an angle of minus 31.8 degrees. This now allows us to find that V sub 2 as a complex number is 29.41 at an angle of minus 31.8 degrees. Or we now have 29.41 times the cosine of minus 31.8 degrees plus J 29.41 times the sine of minus 31.8 degrees by Euler. If we now do the appropriate multiplication, we have 29.41 times the cosine of minus 32. Cosine of a negative angle is the same as cosine of a positive angle, and we now have 29 times cosine of 32, which gives rise to 25. Now we have the sine of minus 32 approximately. Sine of minus angle is minus the sine of that angle, and we now end up with minus J 15 approximately. Actually, maybe 15.5 would be a closer approximation. That's now V sub 2. We now know from our KVL equation that V sub S is V1 plus V sub 2. And V sub 1 was simply 480 at 0 degrees, and V sub 2 we just found to be 25 minus J 15.5. That's now V sub S. Well, 480 at an angle of 0 degrees is just a real part of 480 and no imaginary part. We can now add 480 to 25, and we get 500 plus 5, or 505, minus J 15.5. That's now the voltage at the supply side of that circuit configuration that we had before. Now that we have that picture, we can now find that the angle of that is going to be, or if we looked at the polar form of this number, it's going to be, again, magnitude of 505 at an angle of minus 1.76 degrees. And that's now V sub S. The power factor, well, we haven't figured that yet, have we? But now we know what the supply voltage is as either rectangular form, and that's in RMS, or in polar form, 505 at an angle of minus 1.76. Now we know that the current I sub RMS is the same as I1, which is the same as I sub 2, and that current was, in fact, 294.1 at an angle of minus 31.8 degrees. We now know then that the angle of, or the difference in the angle between the voltage and the current, which we could call theta sub S for the theta of the supply, or theta total. That's now theta V sub S minus theta I sub S. Theta V sub S we just found to be minus 1.76 degrees. The angle of the current is minus 31.8 degrees. And now if we add those together, we now are going to take 31.8 and subtract from that 1.76, and we now have an angle of the supply, or the source, is 30.4 degrees, which now allows us to find the power factor of the source side. Or if we now take the cosine of 30.4 degrees, we end up with a power factor of, and this angle is positive, and so that gives us then a lagging power factor, but we now have 0.86, let's say 5, and that's a lagging power factor. And that now completes the design that we had been asked for in that particular problem. Now we could also look at, in addition to what we've been doing, we could actually examine some of the other relationships after having worked the problem. We can look at it a little bit more in depth. We can say, well, with respect to our particular problem, what was the complex power of load number 2? And that's now this Z sub 2, whoops. We can think of it many different ways, but the easiest to begin with might be to say, okay, that's V times I star. Now that we have V times I star, we can write that in other ways. We could say that this is now V times, or what is the voltage? We could say that the voltage is Z sub 2 times I sub 2, and that's times I sub 2 star. That says then that this complex load power for load 2 is its impedance times I sub 2, the magnitude of the current, I sub 2 squared. And that's using this fact that I sub 2 times I sub 2 conjugate, or any current for that fact, or for that matter, times its conjugate, is equal to the magnitude squared. And you can see that if you just say, okay, let's assume that I sub 2 as a complex number is R plus JX. Its conjugate now is going to be, the real part will be the same. We will just change the sign of the imaginary part. Now we simply need to multiply those together. We have I sub 2 times I sub 2 conjugate, which is R plus JX, times R minus JX. We now have R times R plus JXR minus JXR, and we now have a minus JX times JX. the minus jx's in the middle cancel, and we have r squared, and here we have j squared with a minus sign associated with it, and then x squared. So this now becomes r squared plus x squared, which is really just the magnitude of I sub 2 quantity squared. And that now allows us to write, if we know the impedance and we know the current of some load, we can now say that the impedance, or the complex power, is now this Z2 times the current squared. Or if Z2 is now separated into its real part and its reactive part, we can now look and see that the complex power is R sub 2 times the square of the current, that's the average power, plus the reactive power, J, x2 times I sub 2 squared. This is now the average power and the reactive power. If we were to look at our particular case, we would find that since x sub 2 was 0 in our example, we would find that P sub 2 is equal to R sub 2 times I sub 2 squared, but remember, I sub 2 was the same as I sub 1, which is I sub RMS. R sub 2 was 0.1, and we had 294.1 squared, which is a pretty big number. Now we take 1/10 of that, and we end up with 8,605.5 watts for the average power of load 2, which was the transmission line. We know that it had a reactive part equal to 0 VARs, and then we know then that the complex power, S sub 2, was P2 plus JQ2, and that's also equal to V sub 2 times I sub 2 conjugate. And we could do that and find the total complex power. We had S1 was V1 I1 conjugate. V1 was 480 at 0 degrees. I1 was 294.1 at minus 31.8 when we take its conjugate. I'm sorry, that was the current. Now we need to conjugate that. We now have 480 times 294.1 at an angle of 31.8 degrees, or this now becomes 141.2 times 10 to the third at an angle of 31.8 degrees, or that's this 120 kilowatts plus J, 141.2 times 10 to the third sine of 31.8 degrees, and this now gives us the reactive piece of load 1, which was 74,368 VARs. Now we can find the total complex power. That's just the sum of those two complex power. S2 was this 8,000 in real part, 605.5, and now we write down Now let me go ahead and keep everything consistent. This is now 120,000 plus J, 74,368. This now gives us an S total of 128,605.5 plus J, 74,368. That's in rectangular units, and that's the volt amperes. If we convert that to polar form, we end up with 148,598 at an angle of 30.03 degrees, and that 30 degrees for the total load should look very familiar, and we could then take the cosine of that angle because it was positive, we now have a lagging angle. And we could sketch the power triangle for the total system if we wanted to. Here is our complex power magnitude, which was this magnitude of S sub t. We have an angle of 30.03 degrees. This real part, or the total average power, is this 128,605, and the reactive piece is 74,368 VARs. And again, we could find various relationships here and relate those to what we found earlier. But that should be then enough for that two-load problem with complex power. Let's now see how far we can get through the next problem, which is associated with power factor correction. In this particular problem, let's say that we have a load S1 that has some complex power associated with it. Maybe this load is being supplied by a voltage of 230 volts, and let's say this is now load number 1. And maybe somebody tells us something even more about load number 1. Suppose they say that the complex power for load 1 can be described by its average power, or real power, of 50 kilowatts, which, if we were thinking in terms of horsepower, that's 67 horsepower. And let's say that they also tell us that the power factor is 0.8, and they need to tell us what the sign of that power factor is, or whether it's inductive or capacitive. It's lagging, so it's an inductive load. What somebody wants to do is, now in this problem, try to make that 0.8 lagging closer to 1. And the way they want to do that is they want to now introduce another load, or put another load in parallel on this load, meaning let's connect another load, and that we will call load 2, but it has now this complex power S sub 2 associated with it. And the task, or the objective, is to now introduce this load number 2 such that the total power factor is now closer to 1, and let's say it's now 0.95, but it's still lagging. So we're not moving it beyond 1 in going capacitive, but we are wanting to bring the power factor by the addition of this additional load or second load closer to the ideal of 1. Let's now go through one way of solving this. Let's first find out more or look at load number 1 in a little bit more detail. And if you go back to load 1, we were told it was 50 kilowatts. That's the real part, or the average power. That's now the horizontal piece in the power triangle, and we're given the power factor of 0.8. That essentially tells us the angle associated with load number 1. Or we can now think of load number 1 this way. We know that it has a horizontal value for the triangle of 50,000. Here is our angle, and it's positive, so we'll show it as positive. We can now find that angle theta 1, which will help us find the apparent power, or the value of the magnitude of the complex power S1. Remember, we were told that the power factor of load 1, which is equal to cosine of theta 1, was 0.8. That now allows us to write theta 1 is the inverse cosine of 0.8, or theta 1 is now this 36.87 degrees. We can find a little bit more information now that we have these tools. We know that the average power P1 is the apparent power S1 times the power factor, or the cosine of theta 1. That now allows us to solve for this apparent power S1, because we know P1 and we know power factor 1. So that the apparent power is 62,500 volt amperes. And we now know what S1 looks like as a complex number. Our complex power is the value of that apparent power, or the magnitude of S1, at an angle of S1. We just computed the absolute value of S1, or the apparent power, was 62,500, and the angle of S1, which was theta 1, is 36.87, and that's now our volt amperes. And with that, we could now compute, if we wanted to, the value of the reactive power in load 1. This now by Euler is the magnitude times the cosine of 36, and that's 50,000, plus J 62,500 times the sine of 36.87, or that now becomes 37,500 for the reactive component of load number 1. Now what we're wanting to do is let's now sketch what we have. We now have S1 having a horizontal length of 50,000, and we know that we are going up here, so we've gone over there 50,000. We've now gone up there 37,500 for the reactive component of load number 1. What we're wanting to do, and we also know that this angle, theta 1, is 36.87. What we're trying to do is leave the real part alone, not introduce any more real power, but we want to actually go in the opposite direction with our reactive power so that the net effect of taking the black up and the blue down will give us a resultant with a smaller angle, and what we're looking for is this angle for the total, and we were told what the power factor of that total wanted to be. We want a power factor total equal to 0.95 lagging. And because of that, we can now find that angle for theta total. That's the inverse cosine of 0.95, which is 0.1.